Hi Bobcats. In the last video we looked at Le Chatelier's principle and how it applies when you change the amount of a reactant or a product. In this video we're going to look at a couple other changes that you can do to a chemical reaction, such as changing the temperature of the reaction, changing the pressure, or changing the volume. So our objective is still to identify the reaction conditions that shift the equilibrium position of a reaction. We're just going to add to the conditions that we saw in the previous video. In order to figure out how a reaction responds to a change in temperature, we need to consider heat as either a reactant or a product. If we have an endothermic reaction, then the Q value or the delta H value will be a positive number, and we can think of the heat of the reaction as being something that we have to put into it to make it happen, which makes it a reactant. So for an endothermic reaction, we treat heat as a reactant. But for an exothermic reaction, well, that's one that releases heat and has a negative delta H or Q value. So since it's releasing it, it's producing heat. So heat is a product. And so if we can think of the endothermic reactions as having heat as a reactant and exothermic reactions as having heat as a product, we can use the same ideas that we developed in the last video for predicting the direction that the reaction will shift. For this reaction, PCl5 in equilibrium with PCl3 and Cl2, our delta H value is positive, which means it's an endothermic reaction. So I'm going to write heat in as a reactant. So we'll have heat plus PCl5 in equilibrium with PCl3 plus Cl2. And we're asked to monitor the pressure of PCl5 with these changes. The first change is that the temperature is decreased. So think of taking your reaction and putting it into a refrigerator, well, or an ice bath. If you do that and you decrease the temperature, you are removing heat from the reaction. And so if we remove a reactant, the equilibrium is going to shift to the left. It's going to go in the reverse direction, and that means that we're going to increase the amount of PCl5 since it's a reactant. If we do the opposite, if we increase the temperature, such as by putting it on a hot plate or putting the reaction into a furnace, then we are adding a reactant. When we add a reactant, the equilibrium will shift to the right or go in the forward direction. And so that means that we are going to decrease how much PCl5 is present. Changing the volume and the pressure is usually applied to gases. So we're thinking about situations where the gas is in some sort of a movable container, such as a piston in a cylinder or a syringe. So if we have a situation where we decrease the volume or we increase the pressure, there's less elbow room available to the gas particles, and so the equilibrium will shift to the side that has the smaller number of gas particles. If instead we do the opposite, if we increase the volume of the container, like pull the plunger out a bit on the syringe, that will decrease the pressure inside of the syringe, and that gives a lot more room for the individual particles in there, and so the reaction will shift to the side that has more particles. We can also use the same argument to talk about dilution when we're talking about an equilibrium process that's in solution, because dilution is adding more solvent, and that gives a bigger volume for the particles. And so if the particles are at equilibrium and you add more solvent, the equilibrium will shift to the side that has more particles. This diagram is trying to illustrate what happens with the reaction 2A in equilibrium with B, and both A and B are in the gas phase. A is symbolized by the smaller yellow spheres, and B is symbolized by the larger red sphere. And our starting position is this diagram that's here in the middle. Now, if we take this composition where we have 3 reds and 4 yellows, and we decrease the volume, which is what happens when we move over here to the left, by decreasing the volume, that's going to increase the pressure, because pressure and volume are inversely proportional to one another, and that's going to cause this equilibrium to shift to the side that has fewer moles of gas. So notice that over here in the diagram over here on the left-hand side, we have only 2 of the yellow spheres instead of 4, and so that means that we've increased the number of reds from 3 up to 4 as 2 of the yellows converted into a red. So this process of decreasing the volume will shift to the side that has fewer particles of gas. Now if we go in the opposite direction and we increase the volume, that's going to decrease the pressure, and the equilibrium will shift to the side that has more particles associated with it. So you'll see that from our starting position, 2 of the reds have shifted over to give a grand total of 4 extra yellows, because these new conditions will favor the side that has more moles of gas. This example puts together all of the different scenarios that we have looked at for Le Chatelier's principle. We have PCl5 in equilibrium with PCl3 and Cl2. Delta H is 58 degrees. Question number 1 wants to know what direction the equilibrium will shift when chlorine is removed. It'll shift in the direction to make more chlorine to substitute for what we just removed. So that means since chlorine is a product, that this is going to shift to the right. It'll go in the forward direction. If the temperature is decreased, well, delta H is a positive number, which means that heat is a reactant. So if we decrease the temperature, we're removing heat, so it'll shift to the side that heat is on, or shift to the reactant side, which means it's going to go to the left. Number 3 says that the volume of the reaction system is increased. Increasing the volume gives the particles more elbow room, so the reaction will shift to the side that has more moles of gas. So that's going to shift to the right, because the right-hand side has 2 moles of gas, whereas the left-hand side has just 1. And then what happens if PCl3 is added? That's adding a product. So adding a product will cause the reaction to go in the reverse direction to try to use up that extra stuff we just threw in there, and so the reaction will shift to the left. This question is asking about the equilibrium that's established with acid-base indicators. Acid-base indicators are weak acids that establish an equilibrium where the 2 forms of the molecule have different colors. So this particular indicator, when it's ionized, so we have the ion minus, the indicator minus form, it'll be blue. And when the hydrogen ions attached to the molecule, the indicator will be green. So we want to see what direction this equilibrium will shift to if we add base. Okay, well, this is a little tricky, because if we add base to this reaction, base is hydroxide ion, and it will react with hydrogen ion to make water. So adding hydroxide ion, adding base, effectively removes the H plus ions from the reaction. So if we are removing a reactant, the reaction will shift in the direction to make more of that reactant. So it will shift to the left, and we will see more of the blue ion minus. So the correct answer will be D. It'll shift to the left, and the acid-base indicator will turn green.